Okay, so here's a video for class 7. I don't think these will take very long, but maybe I'm wrong about that. These are some statics review problems to try to help with getting reviewed back with statics, right? So it was a long time ago for many of us, I recognize. So I want to be pretty organized. I said be more organized than this. I wrote on my page. Do I want to try to get out of this? Let's see, end the show. Let me see. I'm going to move this up to give myself some more room. There you go. All right. Boom. So we have 900 right here, force of 900. And knowing that the vertical component of the force exerted on the seal, whoops, must be 900. Determine the required right here. And then a corresponding reaction at A. It would be a good note for always to try to find out what the reactions at all of the pins are, because we could be design engineers, and at each joint we would want to know how much load we have up. So we could probably, I could just start working on the problem, or I could systematically pick it apart, right? So we have let me use black for the pieces, and then I'll put other things on there, okay? So we'll start out with an FBD at the spot that we know about. That's going to be this guy right here, this thing. And we'll look at the forces that are possible onto this, right? So first off, we know that we're going to have this, which we could call, if we want, I almost want to call this a reaction. I decided because we're going to put a force on it, and they're calling it a force. We're going to call this F E onto D. Is that where I decided to go? I guess I just decided to call it E. EY. But also, note we have a force that was coming. Whoops, I need to make it a little bit more severe so you can tell it the angle. That right there. I didn't mean to color that in, but let's see. What did I decide to call it? I decided to call it FD. So this is the force at D. I decided to call it right there. So we know that this right here, by the way, is going to be 900 pounds. So it's going to have, you can see that this thing is an angle FD. So if it has, it's going to have a component that's going to be to the right-hand side. And it's because it's at this angle right here, or at that slope, which is going to be, let me see if I can label that. It's going to be 20 degrees. I didn't put this in a good spot. Let me relabel it. 20 degrees. There you go. Like right in there. So that's FD. If it's going to be pushing with a right component, it has to have a left thing backing it up right here. So here's going to be FEX. That's really going to be like the side of this thing. You can think that there might be a little tiny gap in here, some clearance for this thing that moves upwards and down for you. It could be very, very, very small, but it still would be some amount. This is going to be the wall of E pushing back against D, right? And so we can say that the sum of the forces in the y direction is equal to 0. And we're doing that first because we already know the 900. So we're going to declare that upwards is positive. And so for here, we will say that F, well, let me put the number in. I don't need to use the symbol for the thing because I have the number. 900 up minus FD, but only times the cosine of 20 equals 0. All right, so the FD, the full magnitude of it, is going to be 957.8 newtons. And similarly, so now that we have that, we can go in the x direction, declare the positive to the right, and we will say that FD, or 957.8, times the sine of 20 minus Fex equal to 0. So Fex is equal to, we divide through right there. And did I bother to do it is the question. I did not on my sheet because, well, it didn't matter to us, but maybe it matters to me now. 957.8 and 20 times the sine. Boom. Whoop, I'm in radians. Darn. That's what you get for teaching vibrations. You gotta keep doing radian stuff. I wonder how many times I've messed stuff up since then. No, nothing. That doesn't look right. 957.8. Oh, it's still in radians, you dummy. Degrees. There you go. 20 sine. Losing it. Boom. So we're going to go 327.6. We don't really need it, but maybe it'd be good to know how much or put up on there. All right, so we don't have to draw this out if we didn't want to, but we're just doing it for the sake of argument here. We'll do the FBD of this piece right there. There's really no point to doing this. But we're going to have an F, you call it FD. I'm not making a distinction as to what part is onto what, right? So like I said in the previous video, you can make if you want to have a systematic thing, say, okay, well, this is part 2 onto part 3, or part 3, and then the opposite is part 3 onto part 2. So anyway, this is FD, and we can see that up here, this is at joint B, so we're gonna have an FB coming right at it, and because it's a 2-force member, it's in compression. We know that, and we could do this in any way that we want. We could create if we wanted to, we could create a coordinate system that was like aligned like that if we wanted to. We could break the thing down into X and Y. But no matter what, so we do this right here, by inspection, which is totally fine as long as you are right by inspection. When you get it wrong, there's a big problem. So could write just by inspection. Here's the answer at the very end. All right, so lastly, what we'll do, I guess it's not lastly, I'm going to put in a little bit more, but I will draw the FBD. And it's nice, it's just a nice thing to try to draw the piece as it is. I don't think it has to be done, but it's kind of nice to have. All right, so we're going to have this force that's coming down here. This is the thing that we want to find. And they called it P, so we'll begrudgingly call it P. I guess we could also have a reaction right here. I don't know what direction, and we're not putting in the weight of the things because we're going to ignore it. They didn't tell us the weight of the thing, so we're going to ignore it. So here's where I like to go, the RAY and the RAX. Now there's no moment right here, right? So this is not a cantilevered problem, so there's no moment onto the thing. And then we're going to put into this force, I guess. We will kind of we have to be careful with our angles. All right, so that is a force right here, and I can't decide right now, this moment, whether I want to break it up. I guess I will draw it in unbroken up. All right, so here is that force right in there, and that's going to be our FB acting on there. Some of the difficulty in this problem is just getting all of the geometry that we want right there. Right, so right here is our 20 degrees. Is that right? Yes. That's the there's that angle. Okay. This one right here is 60 degrees. And then this one right here is 15 degrees. All right, so What they did, they didn't do us any real favors here by the geometry that they gave us. I'm going to leave these. I'm not going to designate the units. We just know that they're all millimeters, right? So right in here. So and I kind of wish I had made this just a little bit bigger. So I would suggest for you that you make a nice big diagram. That they will make more paper if you need it. So anyway, let's see, in terms of solving our problem. Well, first we're going to do the summation of moments about A equals 0. That is true. We want to carefully find all of the components and all of the moment arms, right? So, and we know FB is equal to FD, so that's right there, equal to 957.8 newtons. So I'm going to try to use some numbers as I come through here, right? So we want to be thorough. So we're taking it about A. So first off, in the y direction, FB in the y direction. So we'll go 957.8, and that's going to be the cosine of 20 degrees, right? And it is going vertically, and that's going to be a rotation about the counterclockwise. So it's positive. We already made it positive. So its moment arm is going to be 200, and we're looking for a force, so we're going to divide through all the way and end up with a force. So it's okay to stay with millimeters right here. This is the 200, but only, and let me draw this briefly here. Let's see, can I put it into a orange? Right, bump, 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 right there. Okay, so you can see that's the distance that we want to designate here. So we're going to take that 200, and that's going to be times the cosine of 60 degrees. Right, so that's the moment that's being caused by the vertical component of FB. Now, also the horizontal component, which is very small, right? It's moving kind of like from right there to right there, right? Just that little piece right there. That is also going counterclockwise. That's not always the case with every problem, so just be aware of that. So that's going to be our 957.8, and it was positive because it was going counterclockwise. And now that's going to be the sine of 20. And now you want to try to have the moment arm for that, right? So it's kind of I'm going to draw it on here, but it really isn't right there. So it's like that is the little component that we're looking at, and so this coming down right here, the 200 times the sine of 60, and I didn't leave enough room to keep going onto the thing, so we have to do a little carriage return, is coming right into there, right? So those are the two parts of FB that have caused this. Now, you might be tempted to just multiply FB times our 200, but it is not perpendicular to this line, right? So that would be like you'd be jumping too quick to a conclusion that wasn't true, right? So we had to do that. We had to break it down into components and then find the distances that were perpendicular to each component. And now we go to P, which is going to be clockwise, which makes sense because it has to balance out. So it's the one thing left here. Now here is sort of a dilemma. I can do this in two separate ways. It's going straight down. So what might be best is to, instead of breaking the force into components, is to find this distance right here. So to find that distance, and I'm adding some additional lines onto here that probably aren't appropriate. So I'm trying to get rid of that guy. Yeah. So this is sort of like an inappropriate little line that I've just drawn onto here, but I could find that distance, and so that would be 200 times the cosine of 60 plus 400 times the cosine of 15. You see that? So that's going to be this distance right here, that 400 times the cosine of 15. And that's going to be this distance. So that's going to be the total perpendicular. And then so we have equal to 0. So we will have P from that. It's going to be equal to 301.7 newtons. I'm not going to bother with finding the reactions at A. That's just the summation of forces in the x direction, the summation of forces in the y direction. But I will say that an important thing to consider is the mechanical advantage. So what we essentially are saying is we took 300 pounds in and we got 900, not pounds, newtons, 302, we'll call it, newtons were required to create a load of 900. That right there, so we could go output over input. I usually think of it. I think I'm saying that correctly. I don't want to say the wrong thing here, the wrong definition. So I'm gonna look real quickly at what my other things say, my other problems. So I want to get yeah. So we want a lot of times it'll be torque, but it could just as easily be forces, in my opinion. So we go F out, but I haven't seen this written down like anywhere. It's been a while at least. So we could say, we basically know that we're going to have a mechanical advantage of approximately 3, right? Because we're going to have 900 is the desired output, 301.7 is the desired input. So if I was going to be really nitpicky, then we have 298.3. No, 2.983. Sorry, 2.983. 2.983, which is basically mechanical advantage of 3. I used 2 more time than I expected in that example. Anything left I want to say about it? Maybe I want to talk a little bit about sig figs, because I haven't in this class necessarily. If you're going to report the answer to this, I think 2.98 is sufficient. You wouldn't want to have too many sig figs because you don't really know for sure that you're able. It's difficult to measure forces. Forces aren't easily measured, and there's a certain degree of, even when you're doing the measurement, the amount of certainty that you have. So when you come in reporting the answer for something that we're like, how many newtons should we place onto this thing? I'm going to think 302 newtons. That's enough, right? That's enough information to give. If you give too specific, it would sound as if though that exactly that was required, and that you know exactly how much that the 900 would be. So there's going to be some variation. So that's enough information for now. More to come.